Hello students, this is Mr. Bornheimer. Today we're going to be looking a little bit at atomic theory and looking a little bit more in depth at some of the ideas that we discussed earlier in the week. Today I want to talk about Dalton a little bit. Okay, now first off, Dalton, if you remember, and if you take just a brief moment here, why was Dalton important? Okay, look left, look right. Okay, somebody say out loud, why was Dalton important? Somebody should be saying something. Okay, great. I'm sure all of you got it wonderfully. Dalton was important because he brought us back atomic theory. He brought the first atomic theory um, to the table. Now, thanks to advancements in science, if we look here, okay, if we look right here on the page, we will see trying to write, but it's not working very well. Let's go ahead and just choose a different color here, maybe a different pen. There we go. Right here, thanks to advancements in science, okay, John Dalton was able to perform experiments that gave credibility to his atomic theory. And one of the things that was really, really important, one of the things he experimented on and improved was point 0.5 here, okay? That different atoms combine in simple whole number ratios to form compounds. If we scroll down in the book here a little bit, okay, and we look at this diagram here, figure 4.3, we see that when atoms combine, they have to combine in whole number ratios. We don't see 4.5 here. We see 4 whole atoms. Okay, and we don't see 8 or 7.5. We see 8 whole atoms. Okay, and they are used to form 4, in this particular case, molecules. Okay, that have both elements A and B. Okay, so you'll notice the numbers, let me go ahead and, the numbers 4, okay, I'm having a hard time writing today, but that's okay. We'll switch to green this time. There we go. The number 4 and the number 8 are whole numbers, and it produces 4 molecules. There are no decimals here. And the idea of this really comes back to the conservation of mass. Essentially, what you'll see here is we have 4 orange, we have 4 orange. We have 8 purple, we have 8 purple. Everything is conserved, okay? Even though the numbers 4 plus 8 equal 12, that doesn't play into the calculation here. It's by number of atoms. There happens to be 4 orange atoms and 8 purple atoms. They produce 4 molecules, but molecules, like compounds, are combinations of atoms. Okay, so the conservation of mass is shown here. It is observed. Okay, so some of the things that you should be thinking of when we're talking about the history of the atom. Now, the real issue with Dalton was how are we to define an atom? What really is an atom? And and we talked a little bit about Sir William Crookes and J.J. Thomson. It was thought of, okay, that if you increase the size of an atom to make it as big as an orange, okay, then an orange would become as big as the Earth. Okay, to give you perspective on how small atoms are. If an atom were as big as an orange would be as big as the Earth. Say it one more time. Think about it. If an atom were as big as your standard orange, not clementines, okay, not grapefruits, standard orange, then an orange would be as big as the Earth. Okay, that's what we're talking about here. That's the size comparison for atoms. All right, now, uh, it didn't take too long for scientists to really start to invent what we call STM. An STM is a scanning tunneling microscope, and you can kind of see that here on the screen near the top of the page. I can go ahead and try to highlight that. I'll go ahead and grab a highlighter. Okay, and a scanning tunneling microscope would be right here. And what it does is it shot electrons, which we know existed. Electron was coined electron in 1897, and credit was given to J.J. Thomson. And when we shoot electrons at atoms, they reflect away from a nucleus because nucleuses have positive charges. Um, or atoms technically are neutral, but they are drawn to different regions, and essentially what happens, okay, is you get this 3D picture of what atoms look like. This picture here on the right hand side is the actual surface, and these peaks here are actual atoms that we've been able to see with scanning tunneling microscope. I actually had a professor at Eastern Michigan University when scanning tunneling microscopes were first invented who went to Radio Shack and built one. It was really he was a really bright guy, one of the funniest professors I ever had. But the idea of the scanning tunneling microscope now has been around for 20, 30 years. Okay, and so it's very and it allows us to actually see atoms. It's quite incredible. All right, so today we in class, which would be if you're watching this presentation, would have been yesterday or Wednesday in class, we looked at cathode ray tubes, and I showed you an example of oscilloscope, and I bent the ray with a magnet. Now, your standard cathode ray tube is like this diagram here, where you have a cathode on this end, an anode on this end, okay, an opening where you can suck the air out, and here's the tube. Okay, and it's just connected to voltage. And technically what happens is electrons will go from the cathode to the anode. Typically speaking, you don't actually see anything happen inside the tube. But they modified the experiment in figure 4.7 and they put a film on one end. Okay, now this film, all right, which was developed right about the same time that Sir William Crookes was around, you'll see his name here. That film allowed us to see the beam inside the tube. All right, and you'll see that it showed up on the film. And if I can go ahead and I'll just kind of show that to you here. Okay, it kind of shows up here and here. There's a little dot, kind of like what I was showing you today. Like imagine that this would be the screen that we're looking at, and there's the cathode ray, and it shoots the beam down through the tube. Now, you have a magnet in this one, you have electric plates in this one, but they both allow us to manipulate the beam. You'll see that it bends. Okay, that's supposed to be the word bends, by the way, just so you know. Okay, so Sir William Crookes and his cathode ray tube, and this is what he saw happen. And this is kind of what gave us insight into the fact that this stream of particles, this stream right here, must be made of some kind of negatively charged particle. Okay, so this is kind of where the idea of the atoms and electrons and subatomic particles was born. Okay, with the use of cathode ray tubes. Now, if we scroll down a little further, okay, what we see here is you'll see a real world chemistry. The cathode ray was actually used in televisions, and we talked about that. And we talked about J.J. Thomson and his ability to find the charge to mass ratio right here. Okay, using this experiment, a similar experiment to this. All right, but it really wasn't until Millikan did his apparatus that we see here that we really got an idea of the mass of a single electron. Now, we had kind of talked through this apparatus in class, and here's kind of how it works. Okay, I'm going to go ahead and pull my pen out here. All right, so here's kind of how it works. You take an atomizer, which is really just a little container full of oil, and you squirt oil droplets down into this container. Now, we're talking oil droplets that are microscopic. I mean, we're talking very, very small oil droplets. Okay, so these oil droplets, they kind of are filtered down this hole, and we see them in a tiny stream right here. Now, it takes a telescope, or what we would consider to be, it's a telescope is what essentially makes things appear closer, but really it's kind of not necessarily a telescope so much as it is more of a microscope. We're able to actually look at these particles and make them look bigger. Okay, and what we see here is that we drop these particles down between a positively charged plate and a negatively charged plate. And as we run voltage, which we find right here, this is what the symbol for a voltage. As we run voltage between the plates, we can manipulate these particles. Okay, and so as you see over here, it said that Millikan observed the droplets with the telescope. He could make the droplets fall more slowly, rise, or pause as he varied the strength of the electric field. From his observations, he calculated the charge on each droplet, and thus he was able to find a ratio use Thomson's ratio to calculate the mass of a single electron. Okay? So this is where we stopped in our notes. Okay, this idea that we were able to calculate the mass of a single electron. The idea of electron obviously being coined to J.J. Thomson. Okay? So we're going to go ahead and move on a little bit here in our presentation today. And I'm going to go ahead and make this a full screen. Okay. And here we go. Okay, so Dalton's atomic theory. Now, we had the idea of cathode ray tubes and Sir William Crookes, J.J. Thomson. J.J. was the man, Robert Millikan, and now we get to J.J. and the plum pudding model. All right, at the time that the electron was discovered in 1897, we knew that atoms existed, and we had a good idea that atoms contained electrons. Okay, but uh, we had no idea that there were any other subatomic particles. So to our best of our knowledge, the only subatomic particle, excuse me, was the electron. All right, and that's what we see here in this diagram. We have an electron here, and we have electrons here, and electrons here. Okay, any of the negatively charged particles. Now, J.J. Thomson, who was J.J. the man, pretty much came up with this idea which he called the plum pudding model. Now, this is a very famous model in science because it was really our first attempt at trying to describe the nature of the atom and the charges. He hypothesized that this was kind of like a blob of pudding. Yes, a blob of pudding. And this blob had to be positive because it held negatively charged particles in the pudding. And he thought that this model, okay, was a homogeneous mixture, or a homogeneous, excuse me. So essentially, it was a homogeneous mixture of negative particles inside a positive blob, like pudding. It wasn't true pudding, so not real. Okay, don't think that he actually thought that electrons are held in place by pudding. It was a little more scientific than that. But the consistency of the blob was kind of like pudding. Okay, so this was the plum pudding model. Now, today, and as you can see from my poster on the orange bulletin board, we don't think of the atom as being like this. We know that electrons exist and they're zooming around and there's a lot of electrons and they're relatively small in comparison to the atom. But there's also other things about this model that are wrong. First of all, it doesn't take into consideration other subatomic particles, which we didn't at the time know existed, but now that we do. Okay, so the plum pudding model actually was very popular in the scientific community for a while. It was our best explanation at the evidence that we had. Okay, which means that it was more like a theory. The plum pudding model was kind of like a theory. It was our best explanation given the evidence of the atom and the electron. Okay, but like all theories, and we talked about this at the beginning of the year, like all theories, it's subject to scrutiny, and part of that scrutiny for this particular model came from Ernest Rutherford. Okay, Ernest Rutherford was born in 1871, and around 1911, okay, so in his 40s, he decided to shoot the atom. Yep, he shot the atom with particles. As a matter of fact, he shot it with alpha particles. Okay, now, alpha particles are a type of radiation. Okay, they are a type of radiation. And there are three types of radiation. I'm going to go ahead and write them down for you, but please understand that there are more types. Okay, um, let's go ahead and do this we'll do it in a light blue. There are alpha particles. Okay, there are beta particles. So these are particles. And then there are gamma rays, which are really just pure energy. Okay, there's three types of radiation. Gamma rays are very dangerous, and that's what the ozone layer protects us from. Beta particles can also be incredibly dangerous, and it's beta radiation oftentimes that powers nuclear reactors and things like that. Gamma radiation is given off anytime you have radioactive decay, which means that you have a radioactive substance that's breaking down. It usually gives off all of this radiation. alpha particles are the kind of are a very popular radiation. As a matter of fact, in this room, I actually have alpha particle radiation that I can do with a demonstration of. Okay, but nonetheless, alpha particle, beta particles, and gamma rays are different types of radiation. Well, Ernest Rutherford had access to alpha radiation. And so what he did is he decided to direct that radiation, those particles, which were tiny particles, he decided to direct them at an atom to see what would happen. Okay, now, and one more thing you should probably know about this type of radiation: alpha radiation is positive, beta radiation is negative, and gamma radiation has no charge. Okay, so, and as I say here, alpha particles have a positive charge. Now, if we go back to the plum pudding model, okay, let me just go back here. If you shoot a positive particle, okay, a positive particle at this model, what would you expect to happen? Right now, just next, saying it to the person next to you, behind you, it doesn't matter. Okay, someone should say something. Okay, what would you expect to happen? Go, say something. Did anyone say anything? Go ahead and say something. If no one said anything, someone say something. Okay, at this point, it could just be getting awkward. So if you didn't say anything, shame, shame, shame on you. But if you did say something, bravo! But here's actually what should happen, right? Let's say you take a tiny little positive particle and you shoot it at a gigantic blob, okay, of dense material that's what you would think of as impenetrable, okay? It'd be like taking a car and trying to running it through a wall, okay? if there was if we ignored the collision and thought of the car as a bouncy ball, technically all of the radiation should bounce away from the atom. Okay, the radiation should hit it and bounce back. Okay, that's what we would expect to happen if we shot radiation at the plum pudding model. Okay, that's what we would, and that's what Ernest Rutherford expected to happen. Okay, under the plum pudding model, the uniform distribution of particles should have allowed the alpha beam to pass right through with little or no deflection. Oh, sorry. I obviously am a little rusty on my terms here. Okay. Technically speaking, ignore what I just said about JJ and the plum pudding model. All right, I apologize. And here's kind of what Ernest Rutherford thought would happen, right? Because it was a uniform distribution, okay, of particles, he thought that the particles would pass right through. Kind of like if you were to just kind of walk through a crowd of people, okay? You might bump into them a little bit, but technically you could pass right through them, okay? So that's what he expected to happen. Okay, it's my bad. And bam! Collisions and deflections. All right, what happened was, what I originally was talking about was that there was deflections, not little ones, but major ones. Now, Ernest Rutherford had originally thought that the particles should pass right through, and they didn't. Okay, what happened was they were deflected backwards. Okay, which means this. Okay, which means that there had to have been tiny particles that, let's say that here's the atom. There had to be there had to be a really strong positive charge in the atom such that when this positive charge got close, it was reflected back very quickly. Okay? This is kind of what happened. I'm going to go ahead and insert a blank slide. Okay? So that we can kind of get a better picture of what really happened in this experiment. You have an atom. And originally, here's the plum pudding atom, and it was thought of being evenly distributed. And when you shot the alpha particles, Ernest expected that the alpha particles would pass straight through. Okay, this is what he expected to happen, contrary to what I was originally saying, and I apologize for that. But what he found was that particles that were passing near the outside would go through, but particles that were passing closer to the center of the atoms were shot backwards. Okay, now this backwards deflection, okay, means that these positive alpha particles were being deflected by a very strong positive object in the center of the atom. Now, you can probably start to guess what very strong positively charged object was at the center of the atom. Okay, and if you guessed right, it would be the nucleus. Okay, we didn't necessarily know that the nucleus existed. We had no idea that there was this strong positive charge in the center of an atom. Okay, so Ernest Rutherford is credited with the discovery of the nucleus through his gold foil experiment. And what we're going to go ahead and do is there's a video of the gold foil experiment. We're going to go ahead and watch that video briefly here. I'm going to go ahead and find it. Let's go ahead and go back here. If you go to my website and you go to if you go to useful class documents and you go to unit 4 for chemistry, what you will find is that there is a video here. And in this video, they have the gold foil experiment. Okay, and I'm going to go ahead and just have you watch this experiment for a moment. Okay, so we're going to go ahead and watch this. Give me 1 second so that I can get the volume set so you can actually hear it in this recording. Hopefully you will be able to hear it. Okay, and here we go.
The nucleus of an atom was first discovered when a beam of positively charged particles emitted from a radioactive source
Oh, sorry.
aimed at a fluorescent screen. The particles caused the fluorescent screen to glow. When a very thin sheet of gold foil was placed in the pathway of the particle beam, a few particles were deflected to the side. Occasionally, particles were deflected straight back. But nearly all particles passed right through the gold foil, as if it were not there. The scientists concluded that atoms must be mostly empty space, and that because some particles are deflected, there must be a small positively charged central mass, which they called the nucleus.
Okay, so it was this experiment, the gold foil experiment, that allowed us to discover the nucleus. All right, now, because we found this small, dense mass at the center of atoms, and because we now knew there were electrons, we knew that atoms were primarily made up of empty space, as indicated in the video. Okay, this was quite an important discovery. Like all of the discoveries in this chapter that we talk about, they're all really crucial at getting us to our current understanding of the atom. Okay, so here's what Rutherford came up with as this model for the atom. He came up with this idea that we had electrons, okay, and that there was this really strong positive charge in the center. Okay, we thought it was just a single dense single dense region. At this point in time, we had no idea to think that there could be actual multiple particles in this region. So this is Rutherford's model of the atom, and this model of the atom held true for close to 20 years. Okay, in 1911, he did this experiment, and we didn't actually figure out that the center of the nucleus was any different until probably the late 1930s. Okay, so this model held true for close to 20 or more years. This was our understanding of the model of the atom, and it was through this understanding of the atom that we went through World War I. Okay, it wasn't until some later discoveries of the atom that eventually led to the atomic bomb and the splitting of hydrogen, which we are going to go ahead and discuss in a little bit. Okay, um, so yeah, so I'm just kind of going to do a time check here. We're 24 minutes in. Okay, so this was Rutherford's model of the atom, and it was, like I said, the model of the atom for about close to 20 years. Now, Rutherford had discovered the nucleus and had figured that it was composed of all the positive charge in the atom. He concluded that the nucleus was composed of recently discovered positively charged particles called protons. Okay, so it took some more work, but he was able to really look at and kind of coin protons. Okay. Now the protons and electrons were the two subatomic particles that were identified first, and they were the primary subatomic particles in science for a long time. Okay. Now the nucleus to give you an idea of the size of the nucleus. If you were to look at the dot on an exclamation point on a 12-point font, okay, that dot would have the mass of 70 automobiles. Okay, the nucleus was an incredibly dense region, denser than almost anything else that we know of. All right, so when you think of something that's really dense, like metals, or maybe you think your brother or sister have a really dense skull, or something like that, when you think of really dense materials, okay, I want you to imagine then for a moment, take a step back and think that if we had an exclamation point on a sheet of paper and we could fit 70 automobiles in that exclamation point, and we're talking just the point, not the little cool little line above it, the point. So if I have an exclamation point, it's the point. If you could fit the mass of 70 automobiles in that point, that would be about how dense the nucleus of an atom is. Okay? To give you another example, if the atom had a diameter of 2 football fields, the nucleus would be a nickel in the center of that diameter. Okay, so there is a ton of empty space. And we also gave the example that if the nucleus was an apple, the next closest electron would be a mile away. Okay, so this gives you an idea that the atoms are almost all empty space. And almost all of the matter is condensed into really, really tiny, dense region, which we call the nucleus. And the very small fraction of the mass, okay, is actually contributed to the electrons, which are zipping about the nucleus at super high speeds at various distances. Okay, so all of this was kind of figured out in the 1911s with Rutherford and Thomson working together to come up with a good model of the atom. Okay, and we kind of already looked at some of these things here. Let's go ahead and see if there's any other resources here that we want to look at. I'm going to go ahead and just close this out. Okay, we're going to go ahead and look at atomic structure here. Okay, it's another video.
If you could see an individual atom, it would appear to be a solid sphere. But if you could take a closer look, you would see that an atom is made up of a few particles and a lot of empty space. The outer part of the atom consists of negatively charged particles called electrons. Electrons move in energy levels around a central group of particles called a nucleus. The nucleus is made up of particles called neutrons that have no charge, and protons that are positively charged. The number of protons in an atom tells you what element it is. Almost all the mass of an atom is in its nucleus. The total number of particles found there is the mass number. If a neutron is added to an atom of the same element but with a different mass forms. Atoms with the same number of protons but different numbers of neutrons are called isotopes. However, if the number of protons is changed, an atom of a different element is formed.
Okay, so there was some information that we haven't necessarily discussed yet in that video. And one of the things about that are some of the terms mass number, proton, and the neutron, which we haven't discussed either. Okay, if we go ahead and look at the textbook, let's go ahead and pull it up here. Chapter 4. Okay, if we go ahead and look up here, we can see JJ's plum pudding model in the text, but we can see a timeline here. Okay, in 1897, using a cathode ray tube, J.J. Thomson identified the electron and determines the charge to mass ratio. Okay, and then in 1911, with the gold foil experiment, Ernest Rutherford kind of discovers the nucleus. And he's able, with his experiment, to find the relative size and density. Okay, now, it is only but a couple years later, 1913, that we're going to look at the Bohr model of the atom, and we're going to get there in a little we're going to get there a little later. But I want you to kind of take a leap ahead here to look at 1932. That's when this guy by the name of James Chadwick proves the existence of neutrons. We didn't know neutrons existed until 1932. Okay, we knew about the nucleus and the electron much earlier, but 21 years later, James Chadwick figures out the existence of neutrons. He actually won a Nobel Prize for his work on the discovery of neutrons. Okay, if we scroll down a little bit, we see what should have happened had alpha particles been shot at a plum pudding model. And like I said, I did a bad job of explaining this at first. I hope that you have a good understanding of it now. Alpha particles, had it been a plum pudding model, should have gone straight through, like the arrows indicated. Okay, because everything would have been evenly distributed. It would have been like walking through a loose crowd of people. Okay, but when Ernest shot this alpha beam through the gold foil, as we can see here, some of the particles behaved like he thought they would. Minor deflection here, straight through, but then some shot way back. And it's this one right here. This one, I'm going to go ahead and highlight it because it's that important. Okay, I got to go ahead and clear this ink. It's this one right here that caused alarm. No particles should have hit anything even remotely strong enough to deflect it backwards. Okay, it was this particle and many others like it that allowed Rutherford to hypothesize that there had to be a dense region of positive charge that deflected the alpha particles. Okay, so we move down. Rutherford therefore comes up with this model where we have major deflections here, minor deflection here, minor deflection here. Okay, and as we scroll down even further, we have protons, neutrons, so on and so forth. Okay, so we're really starting to get a better idea of the atom by the early 19 teens. Okay, all right, so we're going to go ahead and we're going to kind of go to the next page here. All right, so to kind of recap, there's Dalton, okay, and there's actually a guy by the name of Goldstein that's credited with the proton, Thomson with the electron, Millikan with electron mass, Rutherford with nucleus. What's missing? Like I said, and we're going to kind of get to that. There's this guy by the name of Henry Mosley. He's actually one of the scientists that you guys should have chosen for today. All right, and he kind of comes into play, and you'll notice that he lived from 1887 to 1915. So gold foil experiment 1911. We're looking a little later in his life. He was relatively young, but he had a lot to contribute. Okay, Mosley is the one that discovered that the nucleus of each element contained a positive charge, hence a certain number of protons unique to the element. Unique to the element. Okay, so now scientists were able to calculate the mass of protons and electrons, and they were able to identify how elements were similar and different. Okay, if you were to go ahead and look at a periodic table, okay, we're going to go ahead and pull up a periodic table here. Actually, that's not the one I wanted. Let's look at this one. Okay, if you were to pull up the periodic table, okay, and it's going to kind of load here for a minute, every element in the periodic table has a unique number of protons. Okay, the number of protons is indicated by the large numbers that we see on the periodic table. If you look at the periodic table closest to the upper left-hand side of the room, the one by the kite, you'll notice that the numbers are green. And if you look at the newer periodic table back by the goggle cabinet, you'll notice that the big numbers in the periodic table, the blue numbers, indicate essentially the number of protons for each element. You'll notice every element has a unique number, and that number corresponds to the protons. It's Henry Mosley who is kind of attributed to this discovery of protons inside the nucleus. He didn't discover protons, but he was the one that said, hey, what if protons are the ones that are responsible for the uniqueness of elements? Okay, and it was Mosley who was given the credit for understanding the uniqueness of each element as it related to the number of protons. Okay, so if we look at the periodic table here, something like germanium, okay, we'll notice that it has a number of 32, okay, which means it has protons, electrons, it has 32. We can see that here. Okay, and if you look at tin is number 50 on the periodic table, SN, and it has 50 protons and electrons. Okay, so there's a lot of good things that are happening. If this periodic table is hard to see, I apologize. If you have Google Chrome, it's a really great app to download, by the way. So just be aware of that. Okay. Getting back to Henry Mosley, though, he worked with Rutherford and he kind of helped to take Rutherford's ideas a step further. Okay. Then there was James Chadwick, and he's going to be the last guy we talk about today. Um, when Rutherford, Mosley, Thomson were working on the atom, unfortunately, they were not able to account for all the mass in the atom. They knew what the mass of a proton was, they knew what the mass of an electron was, thanks to Thomson and Millikan. All right, but they could not account for all the mass. So where was that stinking mass going to? Where was it at? And it's James Chadwick that was like, oh, that's where the mass is at. Okay. And he kind of said it must be for these particles that have no charge, which we call neutrons. Neutral, neutrons, neutral. Get it? Okay. But anyway, because of his work in 1935, he received the Nobel Prize. All right. This was a lot of information to take in, and I hope that you've got a good idea of what was going on here. But this was your presentation for the day. If you have any questions, you can go ahead and email me. To briefly recap, we kind of really looked at, in part at Rutherford, a little bit at Thomson, kind of clarified some things previously. We looked at Mosley, Chadwick, and we were essentially trying to take the progression of Dalton's atomic theory at around the 1800s, and we wanted to see kind of where it ended up right around the time of the Second World War. Okay, so we're kind of looking at 140 years here. And in 140 years, we started atomic theory, and we were then at about the time of the Second Atomic War, really starting to get a good idea of what atoms were actually composed of. Okay, and it's this work, unfortunately, that led to some of our decisions in the 1940s and 50s, but we'll talk about that on Monday. Okay, if you have any questions, you can go ahead and email me. If you know of any cool YouTube videos that you can find on this stuff, you can email them to me. I'd be glad to watch them and maybe include them in my lesson. Otherwise, we are done for the day, and you should maybe take a couple of moments if we have some time, which we do, and collaborate with your partner on some things that maybe you or they can bring to class. There is another video to this lesson, and the sub will play it right following this, and that video will have your group number for your hour and which person you are to study or research. Okay, so that video follows this one. I hope that you enjoyed this lesson, and I will see you on Monday. Thanks for watching.